We are about to start. Now the recording has started. So welcome everybody, and also Polina will accept the people on the way when they are coming in, and whoever is the first one. Anyway, we'll start now. So welcome. Our demonstration event lasts until 3 p.m. CT. So we have a bit less than 1.5 hours, and like I said several times, event will be or are recorded at the moment. And let's go to the next slide. So our agenda is following today. I have a short introduction here, and then we have one demonstration, which has set of demonstrations inside of it. And Vahid will from University will go through the presentation, and you should see if you check the not in a shared screen, but Vahid is the only one who has also the video camera on at the moment. So and then after this demonstration, we'll have a discussion and our estimation that demonstration with the slides before the demonstration will take roughly around an hour to go through. And then in demonstration one, we have 4 different areas that we would like to go through and about emulated environment and risk 5 with the Docker and with Kubernetes and how systems connect, how to build the connections between these elements. And by saying this, it's time to give the floor to Vahid. So please, I'll write the slides per your request. So when I need to change them, you just tell me, please.
Sure, thanks. Hello, everyone. This is Vahid from University of Oulu. I am here for you with the second demonstration of deliverable 6.1. Today we will discuss about a little bit about Chemo, about RISC-V, and after that about systems connectivity. And we will show some examples in a live demo. So please, Matti, next slide. So first, we want to introduce the Kevo environment for RISC-V and ARM64 machines. So please, next slide. So what is Chemo? As I said before, it's an open source emulator. It can be run in any operating system, and it doesn't matter that the architecture of the host CPU, whatever it is, it can be run and emulate other instruction set architecture. For example, it can emulate ARC64, which is for ARM. It can emulate RISC-V. It can emulate any 32-bit architectures. And also, what's important here, it can emulate for us the Xilinx Versal board. So we can have this environment for ourselves to build the tools and the dependencies for the project. So next slide. Okay, so Chemo installation is pretty straightforward for us. It can be downloaded and installed from the source. For example, if you are using Ubuntu, you can download and install it with apt-get manager. For example, apt-get install Chemo system ARC64 is one of the commands to do this, but we don't recommend it. It's also available some binary files for Windows, but we don't recommend it since we want to maintain the integrity of the system and to not produce different versions for the Chemo. We recommend to build it from source, so it has a kit and you can fetch it from its source. And after that, you can build it for your system. And we recommend to use one of the latest version, which is 6.2. And for your information, the version 7 is only recented 1 week before. So in the time that we have the environment, it was the latest version. So next slide. And for configuration, for example, for RISC-V system, you can build it with the target list flag, which is RISC v64-soft MMU, and then you can access the environment with Chemo system RISC v64. And also, you might need some flags to run your system for RISC-V. For example, for RISC-V again, the dash capital M means the machine type, which is virtual. Dash CPU RV64 is recommended. Dash SMP means the number of CPUs, and dash M means the size of memory. And for BIOS, for RISC-V, we recommend to use OpenSPI. So actually, RISC-V works with OpenSPI BIOS. And the next slide. And it's almost same for ARM system, except the type of the machine. I mean the target machine, which is ARC64, except RISC-V 64. And also it has some pretty flags. For example, it has a virtual machine, or for example, in case of Versal, you can write it like Xilinx Versal Virt. And for CPU, for RISC-V, there are two actual working CPU, which one is Cortex A72 and the other one is Cortex
You mean
A52.
ARM64, not
Yes,
RISC-V?
yes,
Yeah.
yes, yes. Sorry. Which is yeah, Cortex A72 and the Cortex A52, which Cortex A52 actually is working uh, with most of the ARM devices, for example, Jetson Nano or Raspberry Pis. And next slide. However, we have an alternative uh, for ARM-based machines. We can simply use NVIDIA Jetson Nano. Also, we can use Raspberry Pis to have the machine with this kind of architecture. So these two pictures I have taken it from the real Jetson Nano, and also the information of the CPU. So as you see, the model name of the CPU is Cortex A57 in not in Jetson Nano. So next slide. And in compared to RISC-V, ARM doesn't have much challenges for us. So most of libraries and applications are built for ARM. It has a living ecosystem since Apple introduced the M1 family CPUs. Most of the applications, for example, Kubernetes, Docker, and any any other applications are moving to be run on ARM architecture. So our challenge is remains in RISC-V. Next slide. So, for example, we want to have Docker or Kubernetes or any other tools in RISC-V. So, what should we do? Next slide. So, we should build it ourselves. We should build it from scratch and compile it with the tool chains that is available for RISC-V based machines. For example, for Docker and Kubernetes family, we should have the Go language runtime in the system. So previously, Carlos Eduardo is one of the maintainer of RISC-V machine and already built the Go runtime for RISC-V. So if we want to have Docker in RISC-V, which we should, we can we can first install the Golang in our system and then build the Docker for our system. And next slide. And building the Docker for RISC-V will provide us some benefits. For example, we can build the image for different tools and applications we have in Fractal. Also, we can push the images into Docker Hub, or we can transfer it locally, or by building a local database or local transfer hub for the Fractal, and transferring the images in that way. And so we don't need any building from scratch, building images for RISC-V from scratch. For example, we already have built PostgreSQL image for RISC-V, and we pushed it in Docker Hub. So if you have a RISC-V system, you can access it with this simple command that I wrote it here. And you can use the Postgres image for any RISC-V. Next slide. Matti, please, next slide, if you hear me. Okay, thank you.
Yes, I do.
And Kubernetes is almost same with Docker. Next slide. It's very similar. It is originally written by Go, so we already have the prerequisite for Kubernetes or K3s in our system. So we only need to build it and use it in our system, which I will show you after these slides. So next slide. Okay, and we move to systems connectivity, and we want to demonstrate some examples of how different components of the Fractal should be connected together, and what we recommend for that. So next slide. So the first approach for system connectivity is that in the left side you see a component which can be run in any machine. It doesn't matter, yeah, and it has an application in that machine, and it wants to generate some data, for example. So here it can push the same data to MQTT server or to Kafka, and then we have some other connectors to MQTT and or Kafka. For example, we have database connections to Kafka, and we have some producer or consumers for MQTT. And they can use the data that is generated by the application, or the arrows here are bi-directional. So if the consumer or database for us generated some data, the application can be the consumer of that data, and maybe it wants to some have processing on data. And what is the advantage of this approach is that we can have a scalable version of Kafka. We can scale it as much as we want. We can scale MQTT server, and also the applications, or I say better, the consumers, or I mean the database and the other applications that we can have. We can scale it very easy. But this approach, I think, has some disadvantages. For example, the data which is produced or consumed by the application, it should be sent or received from two different sources. So we want to have this, we want to avoid this from happening. So we don't want to generate redundancy for the data. And also we want to maintain the integrity of the system, and also the other features, for example, the extendability of the system. Next slide. So the approach that we are suggesting here is to connect the Kafka to MQTT. Also, here we will have the we will have a scalability of MQTT and Kafka as well. But here it will avoid the redundancy that I mentioned earlier, that it will avoid that. Next slide. And also we can extend this approach by providing the MQTT server near to application, and uh, the application sent the data directly to the MQTT, and this can run on any machine. So it can be run on RISC-V, it can be run on ARM64, and also the consumer of data or also the producer of the data can be uh, ARM-based, ARM64-based nodes or RISC-V nodes, which are on the right side of this figure. Next slide. But here is the problem: how to connect the application to Kafka. Next slide. We already have some extensions for MQTT like EMQX. We can use it in MQTT to make the connection of MQTT to Kafka. Also, we have Kafka connector, but the problem with these tools is they are not open source and they are not free. For example, the Kafka connector is built by a company, a Silicon Valley-based company named Confluent. They provide some data-oriented solutions for Kafka. Using Kafka, but we don't want to use their approach. So what we are suggesting here is to build the connector by ourselves. Next slide. So we can build these connectors and develop and implement it by ourselves. For example, we already built the MQTT. We called it MQTT Kafka Bridge. We built it with Python, implemented it with Python, and we used it as a bidirectional message transferring to Kafka or vice versa. And we will have the communication between MQTT and Kafka. Also, we should have the same for the database. Next slide. So as you see in the right side of this figure, we have these RISC-V nodes or ARM-based nodes. The only difference between them is that the ARM-based nodes is using MongoDB, and the RISC-V-based nodes is using PostgreSQL. However, they are they are same in the use. They can use the JSON and BSON format, which already Matti had it in the report. So it doesn't matter that what's the behind, what's in the ARM-based or RISC-V based machines in the database section. What is important here is that we can have this connection to the database. And also, I should say that for these bridges that we drew it here in this in these figures, is that we implemented it with Python. But if we want to have more performance and more speed, we can use other languages, for example, Scala or C++. The point here is that the libraries that is doing this kind of connections between, to MQTT or to Kafka, are built for most of programming languages. I think it was the last slide. Maybe you go next slide. Okay, yes, it was the last.
Yes, indeed, yeah.
Yeah.
I think it's your time to take over the screen now. Let me stop sharing.
Okay, I will share my screen. I have this screen. Okay, I think you see my screen, right?
Yes.
Okay, but before that, as you might know, I already set up the have the SSH to other machines, but to show you that uh, I cannot join with my phone to show you the real system here. Okay, I joined. Okay, here is my desktop to Ubuntu, but since I cannot share the Ubuntu screen in Teams and I don't have the application there, I use this SSH to have the uh, desktop here. And here's my setup. Sorry for being mess. So let us go forward. So uh, first, I want to show you the Kubernetes and Docker. I think I already showed the Docker, so I think I go forward with only Kubernetes, which I already installed it uh, in my machine. So, what I want to show you. Okay, I already downloaded the uh, Kubernetes K3s. We can do the same with Kubernetes. It doesn't matter. It is not very different. So it has this install command, which will copy the this service and which will copy this service Kubernetes services into my RISC-V machine. And after that, after I run the installation, which I already did, we can have the access to Kubernetes and we can connect this machine to a K3s cluster, for example. Or if you download the or install the Kubernetes, you can have the uh, Kubernetes for, I mean, to actual Kubernetes cluster. So to make sure that this node is up and running, I run the kubectl command and get the node information. I mean, in the uh, left corner terminal, you will see the result. And the reason that this machine might be some kind of slow, it's because of the emulation environment. Okay, as you see, the node is working with Kubernetes. Uh, Also, it's same for Docker, so I will uh, run the hello world. And also, I mean, we built the Postgres in the Docker Hub, so you can have it. But I don't want to run the Postgres image in this machine because in this demo I will show the connectivity of Postgres, and I don't want to uh, doing something wrong with the IP addresses of this machine. Okay. Okay, as you see, the Docker and Kubernetes is working fine in the RISC-V machine. Okay, the next step for okay, and before that, before going through, I think I forget to show you the uh, show you uh, the commands that I use to run this RISC-V machine. So I want to go to that directory to show you the commands. So I already uh, put it in this bash file. So as you see, here's the command that I'm using it to run the RISC-V machine. So I just forget to show you this first. Okay, the next step for me is to show you the connectivity that I already mentioned about. So in the left up left terminal, I will run the zookeeper. Zookeeper is one of the dependencies that Kafka will use. So this is the command for zookeeper. Okay, zookeeper is started, and this is a command for Kafka server, which actually use the zookeeper to be run. Okay, and I should say that before going forward, I already write a consumer file in the server to show you the data that it will be uh, pushed to Kafka server. So this is the most simple code that you can write for Kafka to show the connectivity and to show that the data is actually coming to the Kafka. So uh, I just run this consumer. Okay, everything is here is set. Okay, and for the first part to show, I have this application named MQTT. And by the way, the first, I mean, the above terminals are the terminals to my other ARM device. So if I give the LSCPU, okay, as you see, this is the ARM-based device, and also in my bottom terminals, I have the RISC-V. I have the RISC-V architecture. So these are the three different machines. The first machine is this is running the Kafka and also this consumer, and my second and third machine is run on ARM machine and RISC-V. Okay, so move forward with the with the demonstration of MQTT. So a simple application that I had it in mind for uh, showing the connectivity. I already wrote it in Python. I generate some data and I will push it to MQTT. So again, this is the simple. This is the simplest way to generate some data and push it to MQTT. And also, I did the same for RISC-V. So I go to this directory and show you the. Okay, as you see, these are almost same. This is the this is the script to produce the data for MQTT. And then I want to show you the connector. I mean the bridge that we build it for connect MQTT to Kafka. So again, we used Python. In the above machine, which we have the ARM, I want to push the data in Kafka in the topic that it has the name of ARM. So it has a very simple function. So it will receive the data from the MQTT, I mean its local MQTT server, and after that it will after it receives the data from MQTT server, it will publish or send it through the Kafka and into this topic that I already mentioned here. I mean to this topic. And also for RISC machine, it is the same. So, but the only difference is that the topics are different. So the topic here is RISC. Okay. And first, I should run the MQTT to generate the data. And here in the right terminals, I will try to run the bridge, the commands that will send the data to to Kafka. And also I will do the same, and I will show you in the other terminals that actually we are receiving the data there. Okay, so everything is receiving and sending the data. Left terminal sending the data to MQTT, and the right terminals are receiving the data from MQTT and then send it to Kafka. And here in the consumer that we have here, you see the data that Kafka is receiving from those connection, I mean the bridges. So as you see, they are from different sources. So the first is test arm, and the second is test risk. And it means that the whole system is working fine. Okay, I just closed this terminal to go forward with the next connectivity that I wanted to show you. Okay, the next thing is that we have, let me check that I have the code here. Okay, I have the code in RISC-V. Okay, the next thing is that we have the connection of Kafka to the Postgres or MongoDB database. So I already wrote the code for that one. And again, I try to write the code as simple as possible. So I defined two functions to show you the different types of communication. So the first function is that it will send data to Kafka. I mean, it will take the data from the database from Postgres and then send it to Kafka. And also the second function, which will wrote a new data which is generated, which is produced from Kafka, and it will write it into the Kafka. Okay, I mean into the Postgres. But before moving forward, I want to show you the database here. So as I already mentioned, we have the Postgres in RISC-V. So I named the database test for now. Okay. I wrote a simple table named weather, and here is some data that I pushed into this table. So what we want to do here is that we want to pull this data from a database and then send it to Kafka. And here in this terminal, I mean in the bottom left terminal, we want to show you that the Kafka is receiving the data. Okay, so I just run the command. Okay, it just fetched the data and sent it to this. And here, as you see, it received the data from this topic, which the values are different, which shows that this is actually working and taking the real data from the database and sending it to Kafka. And as I mentioned, it's completely bidirectional. I mean, it can be done in other ways. It can receive the data with the consumer that we have here from Kafka and then send it back to the database. And it is not matter that what database we are using. The point is that it can completely communicate with any databases And if you want a language that is providing us more performance, we can easily use a Scala, for example, or any highly available language. And also here about the Confluent, the company that is building this Apache Kafka approaches for data. I have checked it so far, and the only difference between their solution to their solution to ours and theirs is the language that they are using, but it is not open source and it is not free. But anyway, it is something that the engineers can build it in an easy way. So I think I am done for now.
Thank you, Wahid. We are gladfully now we need reserve more time than we have, way more time. And also last time, 1 month ago, this was the intention that we would have in 1 hour slot, we would have time for discussions, but now we have quite much. Now I would like to open the floor for discussions and questions. Whoever wants to ask on whatever. If there are there any questions from any parties that would like to raise at this stage?
Hello, this is Anna from Nickerland.
Please.
Are you going to share the scripts, for example, as a model for the use cases? The scripts.
Absolutely.
Okay.
Yes, indeed. Everything what is shown here, of course, it will be shared.
Okay, because in the deliverable, these scripts are not in there.
You mean what scripts?
For example, the connectors, the bridge.
Yeah,
the bridges.
Yeah, but also, if I may answer, yes, but the idea is that the deliverable shouldn't have the source code of things, and of course they, as we see that it's about architecture implementation, and these are of course available from our fractal, the SharePoint side, of course.
Okay, thank you.
And also, again, as I said before, and we have it in the report, that these are just examples of doing so. So if you want to do the same, you can do it with any different languages and in different machines. So this is just some engineering work.
And also by saying this, what we look for here is that we have two alternatives: have more demonstrations, and have also produced videos how to do these things. And I prefer to have the videos, but also, of course, we have another alternative. But the idea is that we could also something that we could share publicly, share how things have been done. And there's Martin, you have raised your hand. Please ask a question. Martin, can you hear us? So is the hand raised for a reason, or Martin, would you want to ask something from us? Can you hear us? Can everybody else hear me? Can you, White? Can you hear me?
Yeah,
Yes,
we can hear.
Yes, we can
Yeah, we
hear
can
you.
hear you.
Okay, okay. So let whenever he.
Maybe you can hear me now.
Yes, now. Thank you.
Sorry. Maybe it's now a bad connection because of the internal mic. Yeah. So thanks a lot for the presentation and the work you've done. So the question that I have is how we now link all this to our real hardware nodes. Yeah, you worked now on the virtual nodes with the QEMU, with the RISC-V architecture, but yeah, I see some trouble when we now target the RISC-V nodes that we have in our project. So this is the PAL platform and the NOEL5 platform. So what is the plan how to proceed here? Yeah, because I would not expect that these RISC-V implementations that they really implement all the features that we see in the QEMU virtual environment. So there will be lots of work needed to make this available, I'm afraid.
First, using this emulated environment will not bring any other challenges in the software section. And if we
on the hardware, that's the point. Yeah.
In the hardware it has some challenges, and I don't say anything about that. But from software point of view, it doesn't have many challenges. I think it's really hard to say that it will have not any challenges, but it will have less challenges. And also the codes, for example, for the bridges that we demonstrated here to you, is that these codes are machine independent. So the libraries which we used for these codes can be run in any machines. I showed you in the first that we had the same almost same code for ARM and for RISC-V, for example, to have this bridge. So the codes are actually machine independent, but yes, I agree that if we have the real hardware, it might have the challenges, but only for hardware, not for the software.
And also to clarify it, when the hardware, if the Linux operating system is up and running, it's also an abstraction layer, and this is exactly the same when we have the emulated environment. And also in emulated environment, we define that the CPU architecture is exactly the same, and therefore when it have been delivered in QEMU, it's the code base instructions are exactly the same. So it means that they run, but always when you implement something in a real machines, you might get something that was unseen, but therefore also it means that this is something, the bridge between the work done here and also in VP 3, 4 and 5 and 3, 4, 5 and 6 all together, all these what we have done. Now we have use cases like in VP 7 and 8. It's important that we heavily collaborate, and also like for University of Oulu and Haltian as an example, we have quite much work also in VP7, and the idea is that next step is to have all this work done to be integrated into use cases, and sooner the better. And this is what we want to do. And also, you still have your hand raised, by the way, if you want to put it down or keep it up. You have any more questions?
Yes.
If not,
maybe we have Frank here in the line, who is the one who knows best about the PAL platform. So maybe, Frank, the question to you: what is your opinion when you think of, for example, the Ariane core? So what will be the challenge here to run these things that run on QEMU in the real hardware then?
Yeah, I mean, Ariane should not be an issue.
Okay.
The question is, I mean, there is nothing in this part that is hardware relevant, right? I mean, if you assume that all this infrastructure runs, it doesn't matter if you are running it on an x86, an ARM, a RISC-V, whatever. But the question is more, you know, essentially the example there is maybe too simplistic, right? You're passing a text message to a database over the internet, right? And for that, you need Linux, you need this, you need this, you need this, you need this. That's a ridiculous amount of software overhead just to send a small thing. It would make sense, obviously, if the system that is doing that is you know, doing a lot of things. But if you have like this tiny sensor node that is fitting, I don't know, in a corner of like a button of your shirt, and it's, let's say, collecting temperature values, it probably doesn't need this sort of operating environment. Let's say the smaller pulp nodes are more for that kind of application. And if you now take and say, hey, this is a tiny button that I'm attaching to someone's jacket, and it is every day sending twice the temperature over some network. But it has to run Linux, it has to run Python, it has to run Kubernetes, it has to run this. Then things obviously come to a different level. So people have to be aware of this. I'm not saying this is good or bad. I mean, this would directly work on larger nodes that have the software infrastructure there. And I see zero problems with that. Is it efficient for, let's say, energy efficient for a small application? That's a different discussion to have.
I can add something here to some clarification, but it's just from my knowledge. But I want to share it with you. For example, the reason that we are suggesting to use MQTT is that it is not dependent on the host operating system. If you can have any socket application, for example, you can have this tiny Cortex M37, I think, machines, and you can have the connection to MQTT server and sending the data directly to that without having any operating system layer or any, any energy consumption things that are pretty much powerful, but they are useless in our case. So it depends. It really depends that what you have intention to do, and the reason that in the approach too that we put the MQTT near the application, I mean in the operating system of the application, is that we make the MQTT server more close to the edge, to the end nodes that are actually using or producing the data.
And there is still Alexander, you have a hand raised.
Yes, thanks. So I just wanted to add to what Frank has said. He was like more on the focus of the small scale systems for once, but even for a larger scale system like Verso, you would have to think two ways. Like one way is the integration of all of this based on the given platform, even though it may be just engineering work, is still somewhat heavy lifting for the levels of like package 7, and everybody has to choose what to choose from. So it would be quite valuable to work on that together easily, because then we would really be able to see where the limitations go. I think we from PLC2 are already quite aware that it may make more sense to go to a standard Linux distribution than stick with the better Linux and try to modify that to incorporate all of that. It will just be a pain. But I'm not quite sure about that. And of course, the other work package 3 stakeholders in the platform will also have their share on that level. But that's the first thought. The second thought then goes along with what Matthias was mentioning before, when it goes into these lines of accessing the hardware. There's a tremendous amount of direct interaction with the hardware that requires kernel accesses, that has very different driver architectures, that in the end really exposes certain elements that you may want to control in a rather closed application. And for us, the question is, of course, pretty important. Do we suggest a certain escape mechanism out of the Dockerized, containerized applications into the hardware, or do we just leave this open to the work packages or to the use cases to do as they like? So that's really something that is, of course, concerning from our platform perspective. So these are the two things that I see there.
That's a really good comment, because do as the like. The approach is that these are examples, and also how things can be containerized, and also of course other approach is not to put them as a containers, and then also do them locally, or also what to do to local. It means that when we have the whole environment from sensor to the cloud, it means that what elements are doing in which layer. Sometimes the gateway is just passing through the data, or doing just some simple analysis there, then passing through the information out, and it's it's depending on the use case how heavy pattern or we are using on the edge which are needed. But to have the holistic approach, all these layers have to, when we build the demonstration, also architecture, that we have everything needed there, and it's per use case needed elements are used, and there are also alternatives as well how to use them, but also there is alternatives what to not to use and what not to use and what to use. So with this openness, as it was written in our plan, and also that in for when we are building the fractal node, means that when we leave this openness in place, that you must use this, you must do this. The idea is that we bring the way that this is how you can do it, but of course they are very you can vary from the approach. But the idea is that basic building principles has been containerized everything you can and keep things as standard as possible. And also I think one of the key findings have been that even though we have only handful of boards available for RISC-V, it's rather well we can implement the same features to RISC-V as we can do with ARM64. And this is one of the key findings that we have had. And then also, for sake of clarity, if I take the screen, this is something that it was not that well. I think that I did not mention it. I want to highlight it again here. So if you can see the screen, so there was no such thing that Postgres image in Docker for RISC-V. So this has been built by our program, and you can see under this Docker pull, this you can find this on Docker Hub. So it means that we created something that did not exist, or somebody hasn't just done it. So therefore we put it there as well as an example. But this means that all in all, when we go back to the topic that it's important to start the integration with use case 7 and 8, and we know that there might be something that we have to, some elements could be added there on the way, but our idea is that when we build the deliverable, we also put undefined services there and also explain something that we need per use case, which is not well, they are just add-ons that you can, for whatever application you should be able to add to the architecture. So architecture as such is not closed; it's functioning, but it means that it has to be the way that it also flies 5 years after the program as well. Hopefully, this answered your thoughts. Any other questions, comments that you would like to go through? And also it's after the first demonstration, we got good 2 different persons connected us at how could we go forward and test things. And also this is something that I want to highlight, that we are more than willing to collaborate when you have the RISC-V hardware. Let's start putting these things as soon as possible there in use cases as well, that we really have the results. The sooner we have results there, the better as well. But also this means that if there are any topics that you would like to have the demonstration about, even though we are closing most likely task 6.1, it means that of course if we can do those under VP7, or in every case it's valuable for us to demonstrate the knowledge that we have, that we can share it. Just if you want, just drop me a topic that what you want to be demonstrated, and we will do it. And this is, and also this, I think this, and then Vahid and I, we are of course available for how to go forward, and we can even have the RISC-V the separate meeting, and let's start integrating the results to use cases where RISC-V is needed, as an example. But this is also a topic that we can tackle in VP7. But the idea is that I have said it several times that now it's time to start doing it. then we have the functioning architecture in place. So any questions, comments, thoughts? And now when we have reserved 1.5 hours, we were able to do it 1 hour, but I think this was a good idea to extend it anyway. And then that was raised, it was the half an hour extension was raised in our PCC meeting. And I think that was a good idea from I think it was a program coordinator, Isaiah, who highlighted that. So now it's time for last time. If you have any questions now, it's time to shoot. If not, we are about to end our presentation and also seems like not. So thank you for the participation and looking forward to seeing you in person when we have a face-to-face meeting, and also looking forward integrating the results to use cases. Thank you everybody and have a nice day.
Thank you.
Thank you. Bye.
Thank you.
Bye.
Bye.
Thank you. Bye.
Thank you. Bye.
Thank you. See you. Bye.